Okay, so let me work out the helical gear design problem. And by now, we have worked out quite a few helical gear design problems. So we should be fairly comfortable in design. So let me take this helical gear design problem. And at the end, I would like to give you some hints on design of shafts, and I will try to solve the shaft design problem. So the problem goes something like this. So in this problem, we have to design a gear pair. Gear pair, it's used to transmit power is equal to 22 kilowatts. The drive gear or the input is 1800 and input is equal to 1800 RPM and output is equal to 600 RPM. So the reduction ratio is 3. The helix angle is 30 degrees. And the profile is 20-degree full depth. So one thing I want to tell you about the helical and spur gear. Typically, spur gear and helical gears are can be replaced by the same equivalent helical or spur gear. What it means, say for example, if you have a gear pair and in that gear pair, one gear breaks down. So what you can do is you can just go and purchase off the shelf replacement gear and it would be just dropped in the replacement. It can work for the worm gears as well. However, for bevel gear, it is always recommended that you replace the entire gear pair. So that is something that you should keep in mind. Because of the meshing, usually the helical gears and spur gears can be mass produced, but the bevel gears are typically produced in pair. And if you buy a commercially off the shelf helical gear to replace just one single gear, it may work, but eventually it would wear down. So that's why they say if you are trying to replace a bevel gear, it's a good idea to replace the bevel gear in pairs. Now, the material for the gears is cast steel. And then the static stress, sigma static, with it's 50 Newton per millimeter square. And in this case, it's given that the circular pitch let me show you what that is. Pi times m, which is the circular pitch, is equal to 4 times, I mean the face width, circular pitch is pi times m, and the face width b is equal to 4 times pi times m. So this is circular pitch. And I want you to think about it for this relationship. If you look at pi is 3.14, so approximately b is equal to 12.5 times m. So that's what this relation means. Now, additional information that is given is the overhang for each gear is 150 millimeter. Now, what that means is here, as soon as they talk about overhang, they give us some hints about how the gears are mounted. So what that means is you have the small gear or pinion and you have the big gear, and they are cantilevered. They could be cantilevered on one side, they could be cantilevered on other side. So this is how the gear configuration is. And this distance is 150 millimeter. And that could be some geometric consideration. For example, that gears needs to fit inside an automotive transmission, and that is the maximum space available to us. The next thing is the shear stress, tau max, is again 50 Newton per millimeter square. And this shear stress is needed for shaft design. Additional information is the Lewis's form factor is given as 0.154 minus 0.912 divided by TE, where TE are the equivalent number of teeth, and last but not least, velocity factor is given as 350 divided by 350 plus V. So it's good that the velocity factor is given so that we don't have to go through trial and error to find the velocity factor and reiterate the design. Now, first and foremost, let me ask you this. Since the gear and the pinion are made up with same material, what would be designed? What should be designed? In other words, whether the gear is weaker or the pinion is weaker, what should we design? Looking at the chat window, just tell me what should we design. So remember the note, when gear and pinion are made with same material, we design pinion. Perfect. The pinion is the small gear. Now, so first and foremost, power transmitted is 2 pi nt divided by 60. Since we are designing pinion, this n and t should correspond to pinion. So what we should do is 22 kilowatts is equal to 2 times pi times the speed is 1800 multiplied by t divided by 60. Now, and the reason for that is input side speed is 1800, and then we have this big gear that is on the output side that is rotating at 600. So the velocity ratio or gear reduction ratio is 3. So 1800 on the input side, this is the pinion, and this is the gear. So with that, if you find out the value of torque is about 117 Newton meter. And the torque will be in Newton meter because the power is in watts. Now, at this point, what we want to do is we want to think about the design approach. Now, at this point, there are multiple ways to proceed. So in this problem, if you look at it, they have not given us the number of teeth, but we know that the minimum number of teeth to avoid interference is anywhere between for 20-degree full depth profile is greater than 20. So I'm going to assume, number of teeth is equal to 24 to avoid or minimize interference. And this is a design criteria. So you can choose the number of teeth. Many a times, if the design constraints are not given to us, you can look at the design data book and find the appropriate number of teeth. So I'm just gonna start with 24, and my argument is gonna be is if I were to go any less than that, possibility of interference is high, since we are using, especially we are using the involute profile. Next step is I want to find out TE, which is equivalent number of teeth. And that is 24 divided by cosine cube 30. Now, how do we decide the helix angle? Helix angle actually depends upon the amount of strength we want in the helical gear. Because as you can see, if the helix angle is too small or if helix angle is too big, that won't work well from assembly point of view. So you want to come up with some sort of reasonable helix angle so that not only the gear is strong, you have sufficient face width, but the engagement and disengagement is smoother. So with this, if you use your calculators, your number of teeth are going to be 37. Now we need to find out the form factor. The equation is the exact same for spur gear, except we are going to use equivalent number of teeth minus 0.912 divided by TE. Substitute the value and you will get 0.12. So we got the Lewis's form factor. The next thing is I'm interested in finding out the module. And as we know, so before we proceed, I just want to talk about the equation that we are going to use to find module. Equation that we are going to use is the WT equation, which is sigma naught times CV, which is the velocity factor, multiplied by D, multiplied by pi, multiplied by M, and multiplied by Y prime. So I'm going to take a moment here to kind of outline what are the knowns at this point and what are the unknowns at this point. So sigma O value is given to us. Now value of B, as we know, B is 4 times circular pitch. Circular pitch, which is 4 times pi times M. So what I could do is I could substitute value of B as 4 times pi times M, multiply that by pi times M, multiply that by 0.12, and sigma O, if you look at the statement, problem statement, is given to us. Now, the unknown in this equation is CV. So the question here is, how do we solve this problem of CV? CV is the velocity factor that depends upon the pitch line velocity, Vp. Pitch line velocity is pi times d times n by 60. So side note for CV, we need to find out the pitch line velocity Vp. And d, we are trying to find out for pinion. So I would say pi times module multiplied by the number of teeth for pinion multiplied by 1800 divided by 60, that gives me Vp. I'm going to explain this equation once again. So please understand, we are doing calculations for pinion. So when I'm looking for pinion design, this is the diameter of the pinion, this is the speed of the pinion. And from the equation of diameter, we know diameter, or also called as the pitch circle diameter, is number of teeth multiplied by n. And a word of caution here, this is not equivalent number of teeth. This is just the regular number of teeth. So in our case, we are not going to use 37, but we are going to use 24. So once I have this Vp, I can find out the value of CV, and equation for CV is given to us 350 divided by 350 plus V. So 350 divided by 350 plus Vp. And please understand, this Vp has to be in meters per second. Now, one thing that I want you to notice, this, depending upon how you choose it, this module needs to be in millimeter, which means the velocity is going to be millimeters per second. So you want to be super duper careful when you calculate Vp, because in CV equation, the velocity has to be in meters per second. So I will make a note. CV is equal to 350 divided by 350 plus V, where this velocity has to be in meters per second. But when I use the equation Vp is equal to pi times d times n by 60, I replace dn by number of teeth, 24, multiplied by module. I'm using module in millimeter divided by 60. So what it means, this Vp is going to be in millimeters per second. In other words, I need to find out this 24 times m divided by 1000 times 1800 divided by 60 as Vp. And this value of Vp needs to go in this equation. So what's going to happen, all said and done, you will have a velocity factor, and you will notice that immediately you will get some, if you don't have the consistent units, you'll start getting some weird numbers. And if you start getting some weird numbers, that is an indication that somewhere the unit conversion is incorrect. So the next equation that I'm going to use is for velocity factor. Once you perform these calculations, you should obtain 350 divided by 350 plus 135 m. And once that is done, this m to start with was in module in millimeters. So next step is take this CV equation and plug it in for the equation of Wt. Wt is equal to 50. I'm just substituting the values. 350 divided by 350 plus 135 m multiplied by 4 times pi times m. This is b. Then we have pi times m multiplied by the form factor 0.12. So now we need to find out the value of Wt. Wt can be found out two ways: torque divided by Vp, or sorry, power divided by Vp, or torque divided by diameter of the pinion divided by 2. Both of them will give you the same answers. So if I were to use the torque equation, torque, because since we already found out the value of torque, I would use 117. I'm using the torque equation. dP is 24 times m. So 24 times m divided by 2. A word of caution: this torque is in Newton meter. This is in millimeter. So we need to convert, for consistency, we need to convert the torque in Newton millimeter. So all said and done, you're going to have the equation for torque in terms of m as 9725 divided by m is equal to 50 multiplied by 350 divided by 350 plus 135 m times 4 pi m 0.12. This equation, as usual, we have to solve using trial and error. And with newer calculators, you can just plug in the equation and then try to find out the values. So when we used to have problems at that, when I was a student, what we used to do is we used to assume a value of CV. So for an example, we would assume the speed of the gear train, which is somewhere between 20 meters per second, use of a baseline value to find to calculate m, and then iterate, go through multiple iterations to find the actual value of m. But with your calculators, once you know how to program this equation, you don't have to do it. So m, once you solve it, it's somewhere 6 millimeters. So the module is 6 millimeter. And to be honest with you, at this point, all the parameters for the gear are designed. So the gear parameters, I'm gonna go ahead and write it down. Face width is 4 times pi times module. Then you are gonna have the diameter of the pinion is 24 multiplied by 6. And we talked about the ratios, addendum, dedendum, clearance. They are all based on the module, and the diameter of the gear, since the reduction ratio is 3 times 24 times 6. And all other parameters can be found out from this equation. So any concerns, question at this point? One thing that you need to do after this step is look at the design and make sure that design is safe for dynamic loading. So step 2 is find out the value of dynamic load. And with that, you should be able to find out the value of VP. Dynamic load is WD is equal to WT plus 21V B C cosine square alpha plus WT cosine alpha divided by 21V plus square root of BC cosine square alpha plus WT. Now, I just want you to refer to the design table, and I will do this exercise for you in this problem. WT is 9725 divided by N, so which is 9725 divided by N. This value is in newtons. Now VP, we already know VP is 117, so pi 24 M divided by 1000. So VP is pi times 24 6 divided by 1000, 1800 divided by 60. So now this value is known in meters per second. This value is known in newton. And at this point, I would strongly recommend to look at tables in chapter 28. So tables in chapter 28. And I will walk you through it for this problem. So if you have the textbook in front of you, what I want you to do is, I want you to go back to chapter 28. And in chapter 28, in spur gear design, if you look at the equation for dynamic load, we want to find out the value of C, and we want to find out the value of C. So I'm gonna give you a minute to look at the table. And the table that you should be looking at is table 28.5 to find value of C. So you should be looking at table 28.5. One thing that we are going to need is 24 pi, which is the face width. Now, if you look at the table 28.5, this is cast steel. So I want you to look at cast steel. So look at material, then it will talk about the gear. So ours is 20° full, and our material, I want you to look at the pinion material and gear material. So I want you to grab the value steel, steel, full depth, and I want you to look at the value of C for different values of correction factors. So E is equal to 0.01, E is equal to 0.02, and so on. And one question that may come to your mind is, what value should I choose? And that's a very valid question. Like, should I choose the error in action 0.01, or should I choose error in action 0.02, or should I choose error in action 0.08? Because based on what value you choose, and I want you to look at this quickly, value of C goes all the way from 114 to 912. I want you to look at table 28.5, please, on page 1040. So look at table 28.5 on page 1020, and you will see for 20-degree full depth, when you have pinion that is made up with steel, you have the gear that is made up with steel. Depending upon the error correction factor, your C value goes from 114 to 912. So at this point, what is the right value to choose? Should I take 112 or should I take 912? And for that, what I want you to do is, I want you to look at the intent of design. So at the end of the day, for design to be safe, the dynamic load has to be less than the static load. Dynamic load has to be less than the wear load. So these are the conditions to be satisfied for safe gear design. So whatever dynamic load we calculate, it should be less than the static load WS, and it should be less than the wear load WW. So my intent is to have this value as low as possible. And one way to achieve a low value is by selecting the lower value of C. And the argument there is, we are going to use the cutter using cutter with E is equal to 0.01. Value of C I'm going to choose is 114 Newton per millimeter. And this is again super important. I want you to look at the units. The units are Newton per millimeter. And we briefly talked about how the math works out. This comes from the Buckingham pi equation and dimensional analysis, something that you want to look at, dimensional analysis. So in that case, you want to be careful that this B is in millimeters, but this velocity is in meters per second. And that is needed, and this guy has to be in Newton. And that is all needed so that the dimensional analysis conditions are satisfied. And when you study dimension analysis, there is something called as the kinematic similarity. There is something called as the geometric similarity. And there is something called as the dynamic similarity. And dimension analysis is a field in itself wherein you can study the large systems by constructing the small systems. For an example would be, say, if you want to construct a dam, clearly you can't test the full-fledged dam because it's not built yet. So what you do is you construct a small scale model of the dam and then use these dimensional analysis equations to test and to study The other thing that is super duper important is in the case of aircraft. Say for an example, if you are uh, designing an aircraft, it is not possible to take that complete aircraft and do wind tunnel testing or test it, or for that matter, even flight testing. So what we do is we construct a small scale version of that big aircraft or big missile and test it. And based on the analysis results of the small scale system, we can extrapolate the results to the large scale system. And that is where the dimensional analysis is super duper useful. The next thing that you might want to think about is you want to construct a part which has wide variations. Say for an example, you want to build a gear that goes all the way from the small gear all the way from this to the huge gear. So it is absolutely impossible to test this huge range of gears. Maybe you can construct a small gear, but you can't construct a very large gear in quantities so that they can be tested. And perhaps your test facilities may not have sufficient equipment or stuff for testing. So now what it means is one thing that you want to think about, and this is super duper important. One thing you want to think about is how can you test very few samples and still able to extrapolate results for a large set of samples. So how do we, so something like a design of experiment. So how do you construct a small subset of samples? So what I would do is, rather than testing 1,000 gears of different sizes and shapes, I will make 3 gears which are representative size and shapes. And I will make sure from dimensional analysis that the gears that I'm going to test, they have kinematic similarity, which is the, if you think about the kinematic similarity, I would give you a sort of a crude example that the velocities are proportional. Geometric similarities, in other words, the dimensions are proportional, and dynamic similarities, which is nothing but the forces, are proportional. So as long as these 3 proportions are maintained, the results that are obtained would be proportionate. So a word of caution, the kinematic similarity may be 1:10, geometric similarity may be 1:5, and dynamic similarity would be 1:1000. So you have scale issues, but the dimensional analysis would take into account these differential scaling and still give you consistent result. And that is where this equation is coming from. And the reason for that is you have different units on velocity, which is in meters per second, and the length unit is in millimeters. So something to keep in mind. So any questions? And you will see this dimension analysis playing a very important role when you design turbines, when you design pumps, when you design internal combustion engines for ships, which are super duper large, or 2-stroke diesel engines for the ships. And I would encourage you to take a look at those. The piston diameter is about 6 to 7 feet for those pistons for diesel engines that drive or that used to drive the prop shaft. So they are huge. If you see the movie Titanic, probably you would have seen the engine room, and that is huge. All right. So with that, I am ready to substitute the values. So I would substitute the value of WT from here, and I trust that you would be able to do that. This value for WT will go from here. Value of V will go from here. Alpha value, as we know, the value of alpha is given to us, which is 30 degrees. Value of B should be in millimeters, which is 24 pi. And then the value of C, we selected value of C is equal to 114. So with this, you should be able to find out the value of WD. And the answer for WD is going to be in newtons. Any questions on WD? The next step in this process is to find out the value of WE. And for that, I want you to look at the equation. So WS, which is the static load, WS is equal to sigma E multiplied by B multiplied by pi multiplied by Y prime. And what I'm going to do is, just like the previous exercise, I'm going to go back and select the values. But before we go and grab the values from the tables in chapter 28, let me just show the next step. Step 4 is determination of wear load. And the wear load equation for the helical gear is WW is equal to dP. Please note, wear load is always for pinion. So wear load is always found out for pinion. And the reason the wear load is always found out for pinion is, if you think about the pinion, the surface stresses on the pinion are significantly higher than compared to the surface stresses on the gear. So you wanna be super duper careful. So dP times B times Q times K divided by cosine square alpha. And we can find out K using two different techniques. We can find out from the table, or we can find out the equation given in the book. The best part of design is we don't have to remember all these equations. We can always refer to the design data book, which is slightly different compared to what we did in high school, where we had to remember all these equations. But in design, you wanna have the reference equations with you. Is normal pressure angle and the equation for normal pressure angle is I gave you that equation, tan Pn is equal to tan phi multiplied by cosine alpha. So what I'm going to do is I'm going to go back to table in chapter 28, and I would ask you to take a moment and go back to the tables in chapter 28, and we will grab the values. So just quickly look at the values for sigma E And I want you to refer to table 28.8. So look at table 28.8. That is on page 1040, 1042. Now this is steel, and the reason I want to do this exercise is if you look at the steel, depending upon the Brinell hardness number, depending upon the heat treatment, the values go from 252 all the way up to 700. So if you look at sigma E, the values go from 150 all the way to 700. So BHN is 150 and 100 and above. So the question that comes in mind is, what value should I check, or what value should I grab when I do the calculations? So for that, once again, let's go back to the intent. What is our intent? Our intent is, as far as design is concerned, WD has to be less than WS, WD has to be less than WW. And that is the reason why we selected the lowest value of C. And the reason for that is maybe we have to use expensive cutter. Maybe we have to be super duper careful in manufacturing, but that ensures that the load, which is dynamic load, is low. Here, what is the intent? WS has to be greater than WS has to be greater than WD. So there is no harm in selecting the maximum value for steel, but you'll make a statement that the steel would have BHN greater than equal to 400, and that gives you the sigma E value to be 700, B value is 24 times pi multiplied by pi. I forgot one M here, multiplied by, so this is B, M is 6, and Y is 0.12. Now, so module is 6 millimeter. So once I do that, it sort of tells me, and you can check this answer, that the static load that I'm gonna get is most likely greater than the dynamic load. And if you have a calculator, please do this calculation and tell me this answer. That way we can assure ourselves that the dynamic load is less than the static load. Next part is finding the wear load. And same thing, in case of the wear load, we have to find out the diameter of the pinion. So let me start step by step. So diameter of the pinion is number of teeth, 24, multiplied by the module, multiplied by the face width. The face width is pi times 6 times 4. Now the Q value, Q is the ratio factor, and depending upon whether we are using internal gear or external gear, the ratio factor changes. Since we are using external gears, ratio factor is given as 2 times VR, which is the velocity ratio, divided by VR plus 1. So 2 times VR, the velocity ratio is 3. 3 plus 1 is 4. So you get this value of Q. Now, next thing is, what is the value of load stress factor? And for load stress factor K, there are two choices. We can use this equation, or what I'm going to do is I'm going to use a shortcut, and I want you to look at this. I want you to look at table 28.9. on page 1040, 1043. So if you look at table 28.9, that gives you the values of surface endurance limit. This gives us the values of surface endurance limit. Now we have a choice. Our surface endurance limit could go from 100 or 150 all the way to 400. Now, I want you, if you have not done already, please look at the table 28.9. And then you will notice, and I will show you what that means. Is sigma ES. Please note, sigma ES is different than sigma E. Goes from 350 all the way to 1050. Now, in the previous iteration, we said that we are going to heat treat to the BHN greater than 400. So I'm going to stick to the same assumption, and I'm going to say that surface endurance strength is going to be 1050 divided by cosine square 30. Now, what is the advantage of this trick? The advantage of this trick is it would make sure that WW is greater than WD, which means the design, and this is super important, is going to be safe. Design is going to be safe. So your iterations or back and forth or calculations will be minimized. Now the next logical question is, it's all great, but what are we losing? Where are we losing? It's like, it depends. So if you are going to increase the heat treatment, if you are going to increase the processing, if you are going to go with the superior materials, the cost of the gear is going to be more. So when you want Brinell hardness number to be greater than 400, if you want, you need to have special purpose heat treatment and annealing processes to make sure that that part is uniformly hardened, and you are going to ensure the case hardness is equal to the core hardness. So that is expensive. But if you are doing paper design, cost is not a consideration, so you can stick to this approach. However, when you go to industry, most likely you will have to take into account the cost of the gear. At that time, you have to select an appropriate mix of case hardness and core hardness to make sure that the design is well within the cost. Okay, this finishes off the basic design. Now, at this point, I want to take a moment and ask you if there are any questions. One variation that you can pursue is you can use these equations and proceed. So typically, when the material properties are not known, you proceed with this approach. But since we are using the standard materials, steel and cast iron, we are okay proceeding with the table values. Any questions here? Any questions on the design steps? The next part is shaft design, and I'm gonna go very slowly in shaft design. So step one is, at this point, I would like to take a moment and note down what we know. We know tangential load. And tangential load is 9725 divided by 6. So 9725 divided by 6. So this is the value of the tangential load. Now, what I want to do is, I want to find out the values of the radial load, and I want to find out the values of axial load. So this is 1621. And to find these values, I have to use the equations from the force diagram. So I want you to review the force diagram that we talked about. If not, I will draw it again. So first and foremost, let's identify what is the pressure angle. Pressure angle is 20 degrees. And then what is the helix angle? Helix angle is alpha, which is 30 degrees. So we want to find out the values of Wn. If you look at the force diagram, Wn is given as Wt tan of phi divided by cosine alpha. And Wa is given as Wt tan of alpha. So if you recollect, we looked at the force on the gear. This is Wn. This force is Wt. This force is Wr. And this force is Wa. So what I want you to do is, I want you to take a moment and convince yourself that the force diagram that we have drawn makes sense. And if you need some additional tools for visualization, note this also is Wr. This, again, since it's the parallelogram, this also is Wt. And the known is this. So once I know Wt, what I'm going to do is I'm going to multiply WT by tan phi, and that gets me the component. And once I divide that component by cosine alpha, I get the answer. So I just want to make sure that everyone is comfortable with this force diagram. If not, I can just show you a sketch. So this guy, and this is WT. If you were to take WT tan C, that gives you in one plane. And then when you divide that by cosine alpha, that gives you in the other plane. So I would encourage you to convince yourself and then substitute the values for WT, WA, and WT and cosine alpha and tan phi. And with that, we should be able to find out the value of Wn and Wa. The next part is quite simple. So we are going to design the shaft for the pinion. So this is the pinion. On this pinion, we have the torque. Then we have two forces, actually three forces. One is the radial force. We have, so actually I made a mistake here. This is not normal, this is radial. This is radial force. This is axial force. And now I want you to look at the overhang. So this is where the gear is supported. So if you look at the moment, and then I'll show you where the WT is. WT is here. So if I show you a three-dimensional view, so I want to show you a three-dimensional view. You're going to have WA, we are going to have WT, and you are going to have WR. And if you think about the bearing is here. So now let's look at the moments that are given by each of those. So there are two ways that this problem can be solved. So you can find the individual moments and then add those, or what you can do is you can find the resultant and take the moment of the resultant. So it actually depends upon how you want to do it. So if you look at the front view, the moment given by WA is in this direction. So moment due to WA is equal to WA multiplied by this distance, which is the diameter. This is super important, which is the diameter divided by 2. This is the lever arm. So which is 24 times 6 divided by 2. Moment given by WR. Here, this is the lever arm, which is WR multiplied by 150. And if you look at the moment given by WT, the moment given by WT, so you need to look at this is WT multiplied by the radius. So you need to find out the moments that are given by these individual components. Let me show you the moment in the three-dimensional view. This is the moment by WA. Then this is the moment by WR. And as you can see, what WT would do is, if you look at the WT is going to give you the moment is equal to WT multiplied by 150. So basically, the moment will be something like this. Now, a word of caution is how do we add or subtract these moments? So clearly, some moments are clockwise, some moments are counterclockwise. So if you were to use the convention that you studied in mechanics of material, one moment is positive, one moment is negative. WA is pointed away. Actually, let me answer that question in just a second. The direction of forces is dependent on the direction of rotation. So basically, if you have a rotation clockwise, you are going to have the forces in one direction. If your gear is rotating in the clockwise direction, you are going to have the rotation in one direction. If the gear is going to rotate counterclockwise, you are going to have the rotation in opposite direction. So what I'm trying to say here is, we don't know in what direction the gear is rotating a priori. So since we do not know the rotation of the gear, we are going to find out the maximum possible moment. So, and I will write this down as direction of rotation is not known or could change. In design, we will find maximum possible moment. What that means is, I'm going to assume all the moments to be positive. So if I were to draw the front view, if I were to draw the top view, and again, you can split it depending upon how you want to do it, but I'm going to assume that this is the axial load. An axial load can go in the left hand side direction or the right hand side direction. So it can go like this, or it can go like this. depending upon direction of rotation. Now WT is going to look like this. So WR, so what I'm going to do, and this is very important, since I have considered the forces like this, I'm going to add, this is very important, moment because of WA and WR is equal to moment WA plus moment WR. This is very important. Since I have considered WR and WA in the front view and WT, which is the tangential load, in the top view, I'm going to add these. Then in the top view, I have MWT. So when I find the moment resultant, what I would do is I would do the square root of, and this is super important, MWA and WR square plus MWT square. Now, if you follow the textbook or some other books, what they do is they sometimes do something like this: MWA square plus MWR square plus MWT square, and then do the square root. So again, that totally depends upon how you are resolving the forces. So the next part is whatever resultant you get, I'm going to call this MR. TEQ is equal to square root of MR square plus T square, and TEQ divided by pi by 32 d to the power 4 is equal to 50, which is the shear stress, T by 2. And from here, you should be able to find out the value of shaft size. So I will repeat the shaft design process once again in a few minutes. So Aaron, did you understand WA direction is not important when we are calculating the shaft design, because depending upon the rotation, your WA could go towards the shaft or could go out of the shaft. But at the end, we are looking at the case when the forces and the moments are maximum, because we want our design to be safe. That's why all the moments we are going to consider positive. So be very careful when you resolve. If you follow the approach in the textbook, they just use the square and square root, and both the approaches will give you same results, similar results, slight difference, but it should, both the approaches are correct. Okay, the last part is just put these gears together and construct an outline for the casing. And you can use the approach for casing design that we talked about in the last class and finish the casing design. With that, we finish helical gear design. Any question, concerns, ideas, thoughts, doubts? And I see I exceeded 1 hour 15 minutes, but no worries, I'll give you a break for 20 minutes and then we will be back, and I would start the next chapter, which is the bevel gear design. But if you have any questions, please unmute yourself and ask me questions.